students, in this video we are going to see a concept of continuous time Fourier transform. As we know, any periodic signals can be represented as linear combinations of complex exponentials, and the phenomena is called as Fourier series. So over here, this term is very important. If a signal is a periodic one, then we can represent it as a linear combination of complex exponentials, which is nothing but sinusoids and cosine, and the phenomena is a Fourier series. But what if a signal is a periodic? So we need to check what will be there for a periodic signal. So what we can say, a periodic signal, repeat. So what we can say, aperiodic signals can also be represented as a linear combination of complex exponentials, but that won't be by the virtue of Fourier series. So I can just write over here, aperiodic signals can also be represented as a linear combination of complex exponentials. But the only thing is that there will be a difference between these two representations, and that we will see now. So whenever I write a periodic signal as a linear combinations of complex exponentials, it is obvious that those exponentials are harmonically related. Whereas for aperiodic signals, the complex exponentials are infinitesimally small. Repeat. The complex exponentials are infinitesimally close to frequency. We need to identify the difference between these two. Here they are harmonically related, means what? It can have a integer multiple of a fundamental frequencies. But over here, these exponentials are very close to frequency. So what will happen? Over here, there is a Fourier series, and that Fourier series we can get for integer multiple of a fundamental frequency which are far away from each other. But for a aperiodic signals, same thing can be written so that the complex exponentials are very close to frequency. So what is the problem? So in Fourier series we have a summation, but because of this, which is infinitesimally close to a frequency, that summation in Fourier series gets converted into integral, and that integral is called as Fourier transform. How this is possible? Now, there is one way where we can consider aperiodic signals as a periodic signal, meaning I can consider aperiodic signal like a periodic signal with time period as infinite. Meaning I can say aperiodic signal is like a periodic signal provided the time period tends to infinity. So if time period tends to infinity, I have a relationship omega as a frequency 2 pi by t. Since time period tending to infinity, obviously omega tends to 0. Meaning what? The frequencies that we will get for aperiodic signal exponentials will be infinitesimally close, and instead of having a summation where I can have the integer numbers of the harmonics, I will get a continuum, and hence that continuum will result into an integral which we called as Fourier transform. So this is a basic fundamental of a Fourier transform. So Fourier transform is evolved in order to represent a periodic signal as a combination of complex exponentials In doing so, summation will get replaced by integration, and this is what we call as Fourier transform. Now we will see a representation of aperiodic signals, that means through the concept of Fourier transform. So for that purpose, let's take an example where x of t is given having a value 1 and 0. It is 1 for mod t less than t1, some constant, that is equal to 0 for t1 less than mod t less than t by 2. So basically if I plot the signal, it will be like this. So for this signal, we are considering this is a time period. So time period is capital T. And for this, if you use a Fourier series expansion, we will get a Fourier series coefficient like this. AK equals 2 times sine k omega 0 t1 divided by k omega 0 t, where omega 0 is 2 pi by t, which we call as fundamental frequency. We can plot this Fourier series coefficient for different values of t in terms of t1, meaning I can have t as 2 times t1, t as 4 times t1, t as 8 times t1. Likewise, I will get the ratio of t to t1. So we will have plot of this ak for different values of t in terms of t1 like this. So now we are getting a plot of AK, Fourier series coefficient for different values of t. So this plot will get, if I have t as 4 times t1, then this plot will get for t 8 times t1, and this will get for capital T 16 times t1. So just these three samples we have considered. So this is a plot of AK and K. Now what we are going to do? We are having a Fourier repeat. Now what we are going to do? We are having a Fourier series coefficient given by this formula AK equals to 2 sine K omega 0 t1 divided by K omega 0 t. So what I will do? I will modify it and I'll make, so I can make AK into T equals 2 sine K omega 0 capital T1 upon K omega 0. Now I can consider K omega 0 as omega, so that we can reduce terms in the expression. So I will get the expression T into AK equal to 2 sine omega T1 upon omega, and this is true for omega as K omega 0. So what we get? This expression we have considered as a samples of an envelope function. And if you plot this envelope function, it will be like this only. Certain changes we need to make. Instead of a K, now I will have a omega. And since this is an envelope function, we will get a plot like this. Similarly, for this, I will get a plot like this. And finally, for this also, we will get a plot and over here we are having this particular interval as 2 omega 0. This will be 4 omega 0 and this will be 8 omega 0. Similarly, in negative side it will be minus 2 omega 0, here minus 4 omega 0, and finally this is minus 8 omega 0. So what conclusion we can draw from here? If I have t very high, that is the case in case of a periodic signal where we are considering it's a part of a periodic signal provided its time period is tending to infinity. So it's a very large time period I'm having. So in that case, what we will have? We'll have all these components very close to each other. So in this anomalous function, all the sample points will be closer. For example, if I have t which is 32 times t1 or maybe 64 times t1, these samples will be even closer. So what we will have? We will have a continuum waveform which tells that will be a Fourier transform, and that cannot be represented like a Fourier series where integers we are going to deal with, rather we deal with the integer only. But in case of the Fourier transform, we get a continuum of a waveform, and that will convert summation into integral. So now in the next part, what we are going to do, we are going to derive an expression of Fourier transform and inverse Fourier transform. Now we are going to derive an expression of a Fourier transform and inverse Fourier transform. For this purpose, let us consider a signal x of t like this. A random shape I am considering. This is minus t1, x of t. So basically what we are having over here, x of t is signals expanding from minus t1 to t1. So basically what I can say, x of t will have some value, we are not bothered about it, but definitely it is equal to 0 if a mod t is greater than t1. So for this purpose, I'm getting x of t as 0, but remaining part there will be some value present. Definitely it is not periodic signal. So I can consider x of t is aperiodic. Can we make it a periodic? Yes, we can make it. So consider I'm going to have a waveform like this, where this particular part will be present and same kind of parts will be present after equal intervals like this. So on and so forth. I consider this is a t by 2 time interval. This is minus t by 2. In other words, this signal now I can assume like this. I will name it as x bar t. So what I have done, I have fit this x of t in this particular waveform. This is a periodic waveform now. Okay. So what I can say, x of t is periodic with time period tending to infinity, and that signal now can be considered as x bar t. So basically at t equal to infinity or at t tending to infinity, x bar t is identical to x of t. So in other words, x of t is periodic with time period t tending to infinity. So now I have a periodic signal whose Fourier series expansion can be very well written. So let's write it. So Fourier series representation of x bar t is x bar t equals summation k from minus infinity to plus infinity ak e raised to j k omega 0 t. This is a standard form of a Fourier series representation. Remember, while considering a time period, we have taken this into account, okay, where a waveform will be starting from minus t by 2 to t by 2. So that time period will be capital T. So I can say over here, this is carried out over the interval minus t by 2 less than equal to t less than equal to t by 2. So this is the interval we have considered for the Fourier series expansion of x bar t. So Fourier series coefficient ak will be 1 by t because time period is capital T, integral minus t by 2 to t by 2 x prime, repeat, x bar t e raised to minus j k omega 0 t into dt. It is simple Fourier series expansion we have done, and Fourier series coefficient is calculated in this manner. Now we know omega 0 is there, and that is nothing but 2 pi divided by time period, which is t in this case. So I can say x bar t is same as x of t for mod t less than t by 2. So just have a look. So it is identical whenever I have this t mod t rather less than t by 2, and x of t is 0 outside this interval. How we are going to represent this? So now I can say this ak, which we have written like this, can be modified as 1 by t minus t by 2 to t by 2. As we discussed during this interval, x bar t is same as x of t. So x of t into e raised to minus j k omega 0 t dt. Now we know t tending to infinity implies x of t is same as x bar t. So I can say now this ak as 1 by t integral minus infinity to infinity x of t e raised to minus j k omega 0 t dt. What we can say now? T into ak, we get minus infinity to infinity integral x of t e raised to minus j k omega 0 t dt. Now we know this t into ak as 2 sine omega t1 upon omega, where omega is k omega 0, and which is nothing but envelope, or you can say envelope function, which depends upon the omega only. So what I can say now, this t into ak as x of j omega, that is equal to integral minus infinity to infinity x of t e raised to minus j omega t dt. So what I will get here, a envelope function represented using x of t. So now I can say this ak is 1 by t. From here it's a 1 by t, and this part is x of j omega, which can also be written as x of j k omega 0. Now we got ak. This ak we are going to substitute in the Fourier series expansion of x bar t. So I can say now this x bar t equal to summation k from minus infinity to infinity 1 by t x of j k omega 0 into e raised to j k omega 0 t. So what I will get here, a Fourier series expansion like this. Since we know 2 pi by t is nothing but fundamental frequency omega 0, so what I can do here, t I will replace by 2 pi by omega 0. So let's replace t by 2 pi by omega 0, so that x bar t I will get summation k from minus infinity to infinity 1 upon 2 pi by omega 0 into x of j k omega 0 e raised to j k omega 0 t dt. So after substituting the value of t as 2 pi by omega 0, I will get x bar t as summation k from minus infinity to plus infinity 1 upon 2 pi by omega 0 into x of j k omega 0 into e raised to j k omega 0 t. Now just a modification, we will get 1 upon 2 pi summation k from minus infinity to infinity x of j, I can consider this k omega 0 as omega into e raised to j omega t multiplied by omega 0. So this is a representation we will get, but what we want a representation of x of t. So x bar t is same as x of t for period tending to infinity, and if a period tending to infinity will get frequency, a fundamental frequency given by 2 pi by t, which tends to 0. And what are the changes happening over here? If the frequency tending to 0, summation will get converted into integral. So what we will do, so x bar t will become x of t, so the expression will be like this: x of t equals 1 upon 2 pi will remain as it is, because all the exponentials are very close to each other. Since omega 0 tending to 0, this summation will get converted into integration with a limit minus infinity to infinity. This will remain as it is, x of j omega into e raised to j omega t, and since omega 0 is tending to 0, so that term won't be there only, and we will get an integration like this. So we will get two important equations out of it now. This is the first equation and this is the second equation. These two equations are actually forming a pair of Fourier transforms. So equation 1 and 2 form a pair of Fourier transform analysis, or you can say a representation. Out of that, this equation number 1, x of j omega minus infinity to infinity integral x of t into e raised to minus j omega t dt is called as Fourier transform. And second representation, x of t 1 upon 2 pi integral minus infinity to infinity x of j omega into e raised to j omega t dt. This considered as inverse Fourier transform. So what we have done, we have derived the expression of Fourier transform and inverse Fourier transform of any signal x of t. Thank you.